Have you ever wondered how tools like Claude Code and Codex gracefully recover from model errors and continue with text execution, while your own custom agents crash at the very first unhandled exception? What if you could lock down these failure modes by building an agentic harness? A deterministic safety net that stays completely under control no matter what the model does. My name is Derick Chen, and this is BuildWithDC. I'm a senior AI development engineer at Google, and previously an AI architect at AWS, where I've led strategic enterprise-grade AI deployments for global customers. In this video, I'll break down exactly how agent harness engineering works, the structural trade-offs, and how you can start applying it to your own systems. And finally, we'll take a look at Claude Code as a live example of these harness features in action. If you're building AI agents today, you already know the basics of prompt engineering and context retrieval. You are likely also familiar with the raw react loops, where a model simply thinks, acts, and observes. These are incredibly fragile. The moment a raw LLM encounters an unexpected data schema or a broken API, the whole loop collapses. This is where harness engineering comes in. The core principle is really simple. The model is the probabilistic brain, while the harness is the deterministic body. Think of a commercial aircraft. The LLM is the brilliant pilot, but the harness is the physical cockpit infrastructure. It is the MCP servers defining your external tools, the sub-agent orchestrators, and the deterministic middleware that keeps the plane in the air, even if the pilot loses focus. So let's look at why simple agent architectures fail in production, and how specific AI agent harness features solve them. Challenge number 1. Unhandled tool error causing infinite loops. If a standard agent executes a blind API call and gets an unexpected error, it hallucinates a fix, retries blindly, and then spins out of control. A production harness solves this problem with both the input and the output guardrails. These are the automated validation loops in popular agentic frameworks, like onTool call and onTool result callbacks. They intercept syntax errors of hallucinations after the agent acts, but before the system crashes, explicitly forcing the model to correct itself. And challenge number 2, the loss in the middle problem. Over long-running tasks, massive tool outputs can vary with critical instructions, destroying your token budget and degrading your model reasoning. A harness solves this with context summarization and truncation. It triggers automated rolling memory summaries when the context hits capacity watermarks, and uses head-tail truncation on massive data returns. This preserves only the essential metadata and error signals, keeping the LLM laser-focused. Challenge number 3, stateless execution. Standard agents forget everything when the session ends, starting from scratch every single time. Enterprise harnesses solve this problem with memory consolidation. By storing all execution trajectories natively in SQLite or vector databases, background agents extract structural insights to automatically generate reusable skills. Your system never makes the same mistakes twice. And challenge number 4, system compromise. If your harness has read and write access to production databases, what's stopping a malicious prompt from commanding the agent to drop a table? A production harness enforces strict sandboxing and privilege scoping. It runs sub-agents in isolated Docker containers and uses smaller, specialized evaluator models to scan inputs for prompt injection attacks before the main agent even sees the text. Challenge number 5, the unrecoverable edge case. What happens when the agent encounters a scenario where the harness mathematically cannot resolve? Or perhaps it intends to perform a potentially dangerous operation. You need an autopilot disengage. A mature harness features human-in-the-loop state pausing. It freezes the react loop, serializes the exact execution context, pages a human developer to make a deterministic decision, and then resumes the execution exactly where it left off. Now, to see all this in action, let's take a look at Anthropic's Claude Code CLI as an example. This isn't just a raw model, it's a heavily engineered harness out of the box. Notice what happens here when I ask Claude Code to execute a task. It initially invokes the standard Python command, but the system throws a command not found error with exit code 127. Instead of crashing or asking me what to do, the harnesses untool results output guardrail intercepts the non-zero exit status, feeds the failure back into the reasoning loop, where Claude immediately self-corrects by retrying the command with Python 3. Now, having to hit an error and self-correct every session is wasteful. This is where memory consolidation comes in. By adding a simple instruction to our project's claude.md file, telling the agent to always use Python 3 instead of Python, the harness automatically hydrates the project context on every launch. Watch what happens on the next clean session. On its very first attempt, Claude uses Python 3 directly. It learned from past experience and eliminated the error entirely. Such self-healing operations can be performed autonomously with the right setup. Finally, let's look at what happens when I give Claude Code a potentially dangerous command: clean up the directory and delete all the log files. Rather than blindly running a destructive remove command, the harness triggers an autopilot disengage. It pauses execution, freezes the state, and presents a clear human-in-the-loop permission prompt asking for explicit approval before any files are touched. These are just a few very basic examples to showcase the Claude harness. If you are interested in seeing more advanced Claude Code workflows on top of the harness, check out my AI DLC Claude Code walkthrough in the link above. And now, to be completely transparent, harness engineering isn't a silver bullet. It introduces serious architectural complexity. You are going to pay a latency penalty for constant state checking and rolling memory summaries. Furthermore, debugging deterministic middleware that is constantly reacting to unpredictable LLM outputs is notoriously difficult. Which brings up a critical question. How do you write unit tests for LLM that might output a completely different reasoning trace every single time? You don't. You build an eval harness. Instead of testing the exact token by token paths, developers run golden datasets through the agent overnight, creating the final deterministic outcomes. So you measure the what and not the how. This is when you need to be more declarative with how you work with AI agents. The moment you move to multi-step, long-horizon, autonomous tasks, this entire infrastructure becomes non-negotiable. So if you're building an AI agent harness, this is what you need to remember. The harness acts as the deterministic body supporting the probabilistic model brain. Input and output guardrails secure your execution flow against hallucinations and rogue loops. Context compaction prevents reasoning degradation over long horizons, and memory consolidation converts transient execution runs into persistent, reusable skills. And lastly, sandboxing and state pausing protects your infrastructure and keep a human in control. Thanks for watching. If you like my content, remember to subscribe to the channel. My name is Derick Chen, and this is BuildWithDC.